Welcome to this video number 8 about active bandpass filters. First, I'll get myself a laser pointer so it's easier to follow. So, normally we start out with the second order low pass filter transfer function. You can see it here. And in order to make a bandpass filter, we use the principle that we can first move the low pass filter up in frequency here, and then mirror this part over here. So then we have a bandpass filter. And the trick is done by that we exchange S in the equation by 1 over delta omega and a factor called S plus 1 over S. And it's mirrored around the mid frequency, and the mid frequency is our, so to speak, compared to the low pass filter, it's our corner frequency. It's the essential frequency we are interested in a bandpass filter, because the 3 dB frequencies down here is the bandwidth, and this is then because we have normalized frequency axis around our mid frequency. They are then the normalized bandwidth. We can see it here. And we have the normalized mid frequency where we have a Q of 1. And the normalized mid frequency is then also 1, because we have normalized it to it. And we also have the factor that omega 2 here minus 3 dB down in the upper part times omega 1, that's minus 3 dB in the lower part, will give 1. And that's due to they are normalized with the mid frequency. The Q factor is the mid frequency over the bandwidth. And the bandwidth we have here normally in the frequency domain when not scaled. It's the higher frequency minus the lower that we are interested in at the minus 3 dB. That's our definition area. So when we scale it accordingly to the mid frequency, we actually divide F2 by Fm and F1 divided also by Fm, and then we get this normalized upper frequency and normalized lower frequency, and this is then the bandwidth delta omega. And since Fm, we also normalize it to Fm, it then becomes 1 over the delta omega. So, how to make a second order bandpass filter? We take the low pass transfer function for the first order. We have it here. And replace S with this equation. And then it's turned into a second order bandpass filter, because these factors replacing S, now when you do that on a paper, you can see it becomes the second order function here in the denominator. When we design a bandpass filter, we have to consider the mid frequency, the gain at the mid frequency, and then the quality factor. And I have to move that bit down. Our mid frequency here is at the center point, and the gain AM is how much this is actually up or down. Here we have a gain of 0 dB. That's a gain of 1. But we can actually have filters where they actually peak up and have some dB above 0 dB. So that is easy to build in a gain factor at this specific frequency. So we have to define, should it just be a gain of 1, or do we need to have some gain at that frequency? The quality factor, remember, that is actually how steep it is, meaning here at -3 dB, should we have that frequency range allowed, or can we only allow this amount of frequencies passing through the filter, so to speak? So using this equation here, the transfer function for the second order bandpass filter, we have it here, and replacing the passband gain for the low pass filter with the mid frequency and delta omega, that's the bandwidth, with 1 over q, we get this equation. So this is the bandpass filter equation where we have AM and the quality factor. So we can easily say, okay, I need a Q of 10, or I can live with a Q of 1, or perhaps a Q of 2 for my design. But that's defined based on the bandwidth and the mid frequency we need to have. For the bandpass filter, we have one specific Sallen-Key topology. And you can see we have here low pass, and then there's a high pass here, and then a feedback. And there's an option to actually have a gain in it. The transfer function for this one, we can see over here. We have something called a G, then the resistor R. You can see it goes in with the same value. The capacitors here also have the same value, but here we have 2 times the resistor. Then we have omega m, that is the mid frequency, 2 times P times F. And we have a second here and a factor, and S here and a factor. So comparing our standard second order bandpass with this equation for the circuit, we can actually see that the mid frequency is 1 over 2 P RC. The inner gain, that's related to the op amp's gain factor here, is 1 plus R2 over R1. We know that from op amp design. And then we have the gain at FM. So that's the peak gain, and that's the gain here, 3 minus the gain. And the filter quality, so the Q of it, it's 1 over 3 minus G. The good thing about this way, this topology, is that we can control the Q via the inner gain, so this factor here, without changing the mid frequency. That's a very nice thing. But we have to be aware, this is the gain at our mid frequency. If this one G here becomes 3, we have 0 here, and then the gain goes to infinite. That is not very good, because then our circuit becomes unstable and could either oscillate or go for the one power supply rail. So either it gives just constant the power supply plus out, or the power supply negative out, so, and it's locked there. And this is a very unwanted situation, so we have to be aware of in this design that the inner gain has to be below 3. Otherwise, we could get instability. Let's find some design equations. So based on this here, we can see that we have Q and AM where G is going into. So by solving for G based on the AM, so solving for G based on the AM factor, we get this equation, and solving for G here based on the Q gives this equation. And then we can, based on that, actually design our circuit. So here we have a small example on how to do that. We have a mid-frequency bandpass filter that has an FM of 1 mid frequency of 1 kilohertz. So here we should have 1 kilohertz, and it should have a Q of 2, so it is a bit more tight than Q1. And we select a capacitor of 1 nanofarad. It's a good stable value. So 1 nanofarad here, 1 nanofarad here. So we have to solve for the resistor and R1 and R2. The first one is easy because the resistor is just calculated based on solving for this one. So we solve this one for the resistor. So we get 1 over 2p FMC. And in this case, we get 159.154 kilo ohm. And the closest one in the E series is 158 kilo ohm. So we select this one. And then based on that, we can we have a Q of 2, and then we can find out what should the gain be of the inner gain be. Based on the requirements for the Q of 2, so we solve for that. We replace in this equation Q with 2 and find out it's 5 over 2, that's 2.5. Then we make it equal to this equation and then solve for the ratio between R2 and R1. It's 1.5. Then we can select a good resistor value here in the kilo ohm range. And I have selected here 10 kilo ohm. And based on 1.5 ratio, then R2 is 15 kilo ohm. And the good thing is both of them are able to become 1% resistors, so they are in the E series already. So this is a possibility. So here we see the overall filter design for the bandpass with these requirements. As engineers, we normally have to check our own design. So when we have calculated it, we do a simulation in order to figure out, okay, is this value here that should be 2 times R selected good enough? Or is there any problems in the setup? Have I calculated it wrong somewhere? That's always possible. When we have simulated, we have to also do a lab measurement, because when we go into the lab, a lot of parasitic elements around the real filter will show up, and then we have to deal with it there. Going physical, so typical filters has to be on a circuit board that are with very short wires and appropriate power supply. Here we don't consider it if it's a battery operated system or we have access to plus minus power supply. So this design could actually happen to be turned into a battery operated setup instead of being with split power supply. Thank you for watching this video about active bandpass filters.